Our next speaker is Mr. Shilei Zhou from University of Technology Sydney, and the title of his presentation is "The Effect of the Tire Dynamics on Autonomous Vehicle Dynamic Control with Wheel Motor in Drive." Dr. Zhou, are you ready?
Yeah. Thank you, Professor. Okay. Yeah, I recorded a video, but I think it's the network is very good, so I can just present here, I think.
Okay, good.
Yeah. I think it's better for us to interact.
Sure.
Let me just share my screen. I'm not sure if I have the right to share my screen because I'm not the host, I think. Maybe if I'm not the host, so I can't share my. Yeah, could you have a check it? Otherwise, maybe desktop. Otherwise, maybe just
they try to
yeah.
put it on the share of the.
Let me see. Yeah. Let me show. Okay, let me show. Okay, yeah, I think it's good now. Share.
Good.
So you can see all of that, right?
You can see. Yep.
Okay, and you can see and hear me. All good?
Yes.
Okay. Yeah. Hello, everybody. Good afternoon. My name is Shilei Zhou from University of Technology Sydney. Today, the topic of my report is effect of the tire dynamics on autonomous vehicle dynamic control with in-wheel motor drive. First is the background. The background is autonomous vehicle is one of the most important vehicles in the future transportation. And besides, the in-wheel motor is also attracting more and more attention because we can just install the motor in the wheel, so we can have the independent torque vectoring control, so we can realize a better handling and stability control. So for the autonomous vehicle with in-wheel drive is really a research hotspot. But there are also some problems. That is, most of the current research on the lateral dynamic control or the autonomous vehicle or the in-wheel motor drive vehicle, they are all based on the simplified models. That is, most popular one is the 2-degree of freedom bicycle model. That is as shown here in the right-hand side. In the model, the suspension and the difference between the left side and the right side, and also the tire dynamics are all overlooked. So this gives us the thoughts whether this simplified model is sufficient to represent the real vehicle dynamics during the lateral dynamics or during the clearing avoidance maneuvers. So this is really a topic we want to investigate, whether this model is enough to represent the real vehicle dynamics. So in this research, we just want to compare a detailed vehicle model, which includes the suspension dynamics and also the tire dynamics and this simplified model. So first, we just build the 2-degree of freedom simplified model. In this model, you can say it's quite simplified because it only contains the longitudinal in X direction, the lateral, and also the rotational directions. So only 3 degrees of freedom, and that's it. So it's really simple. And for the tire dynamics, it's using a constant tire column stiffness. That means the lateral force is only proportional to the slip angle. The slip angle is obtained from the vehicle motions. So for the 2-degree of freedom dynamic model, just these equations is pretty simple. So we just curious about whether this is enough. And to compare the simplified model and the detailed model, we also build another a little bit detailed vehicle model, which in this model, the vehicle body is represented by 6 degrees of freedom. They are the X, Y, Z, and 3 rotational degree of freedoms. And also, we also include the suspension into the model, and also for the tire, because for the tire, it has the longitudinal and also the rotational dynamics. We can't just overlook it. In this model, first, the vehicle body is represented by 6 degree of freedoms, vertical, roll, and pitch first. That means the vertical and the roll and the pitch, they are 3 degree of freedoms related to the suspension. And also, for the lateral dynamic control, there are also 3 degrees of freedom. They are X direction, Y direction, and the yaw direction. This is quite similar to the traditional simplified model. Here, we have 6 degree of freedom, Z, phi, theta. Theta means vertical, and pitch, and roll. And here is a longitudinal, lateral, and yaw. So these are used to describe the vehicle body motions. And here is a point for the tire dynamics. For the tire dynamics, we use a rigid ring tire model. This is used to describe the tire force. In the tire, actually, between the motor and the tire, there is a tire body. It's not a rigid thing. It's a flexible, or we can say it's an elastic body. It means there is force reaction. It's not just when there is a force from the road, the force will be transferred to the vehicle body directly. There is actually a force for the deformation of the tire, and also for the rotational deformation of the pressure, under the pressure, the vertical deformation of the tire. So it's a process. To describe this process, the tire model is represented by translational and rotational springs and dampers. So here, this part is the in-wheel motor, and this part is the tire ring. So between the in-wheel motor and the tire ring is the tire body. The tire body is represented by 3 translational motions, that is longitudinal, vertical, and lateral. And also, for the rotational work, it is also described by 3 rotational springs or dampers. This is a model we use to describe the tire body dynamics. And based on the theory, here are the equations to describe the dynamics between the motor and the tire ring. So here, FCY, TZZ, and FCX, these are force from the road. And when the force comes from the road to the tire surface, it doesn't just go to the vehicle body directly. It passes to the tire body first, and then passes to the motor. And from the motor, because the motor and the vehicle body is actually connected by suspension, so the force will be passed through vehicle body. From this process, we could actually find it's not a rigid body. It's not a rigid body. It's not just a 2 degree of freedom that is simple. It's actually a long process. When the road force is generated, passed to the vehicle body, that means if we just simplify the model, actually, if we just oversimplify the model, the real dynamics is not represented. So by this equation, again, for the motor, it has 6 degrees of freedom. They are the three translational one and 3 rotational. They are X, Y, Z, and the rotational motions around these 3 axes. And also for the tire surface, there are also 6 motions and force acting on it. With the tire road force, we use a brush model to describe them. That is the FCX when the tire has a deformation, and when there is a slip between the tire surface and the road, the force is generated. So we just use the brush model to represent this force. They are mainly the longitudinal force between the tire surface and the road, and also the lateral force between the Y, in the Y direction, between the tire surface and the road. And also, there is a line moment. That is, when we are doing steering, we can feel there is a opposite torque acting on the tire. This is for the vehicle safety. So basically, these three forces are described by brush model. And when the tire road force is the build-up of this process is not a direct process. That means when there is a tire slip, it doesn't mean there will be force directly, and the force will be acting on vehicle body directly. There is also a process, a transient or dynamic process. We use the relaxation length to describe this process. That means relaxation length means when there is a tire slip, the tire needs to roll for a certain distance to make sure the force is actually all fully generated. It's not just generated at the instance when the slip generates. So we use these two models. First, we use this model to describe the tire deformation, and second, we use these equations to describe the tire road interaction. And of course, between the motor and the vehicle body, there are equations here. So from this modeling, we fully describe the force from the road to tire and to motor and to suspension to vehicle body. So this model becomes more completed compared with the single degree of freedom model. So next, we are going to compare. We are going to compare how much difference are there between these two models. So first, we do the simulation. In the simulation, first we do the vehicle dynamic simulation. That is, in the first step, we want to make the vehicle speed to be constant. This is normally what we do in the autonomous vehicle comparison. So here, just a PID. This is not the point of this research. So we just use a PID. That's okay to maintain a constant vehicle speed. And then when there is a required force to drive the vehicle for the speed, the force is allocated to each wheel according to the wheel load, because for the vehicle, the front wheels and rear wheels, they have different load, and the maximum tire road force is proportional to their vertical load. So we want to maximize the tire load friction. We allocate the driving force to the front and rear wheels by their vertical load. And then with this simulation, first, just the differential motor torque is applied to generate yaw moment. That is, when in the front, between the left and right wheels, we generate opposite torque. So the vehicle will just turn because of the yaw moment. And here, from this figure, we can see the front left, front right, and rear left and rear right. They just have the left side and the rear side. They have opposite torques. Then the vehicle should just turn under this moment. Initially, from the yaw moment, we could say in the bicycle model, of course, everything will be just very smooth because there are no dynamics. It's just a rigid body. But in the detailed model, the tire dynamics and suspension, they actually and of course, between the tire road interaction, they generate a dynamic process, a transient process. So we can see it clearly. There is a dynamic process, not just a simple rigid body process. We can see the difference. And from the vehicle body motion, we can also see there is a big difference. From the bicycle model, it's the 2 degree of freedom model, very simple model. We can see no dynamics is shown. It's basically just we put a force or torque on a rigid body and it will move. So no vibrations because it's only a rigid body. And when we consider the tire dynamics, tire vibrations, and suspension dynamics, we can see actually the side slip, vehicle side slip, it actually vibrates. It vibrates. And also, if we look at the trajectory of the vehicle, we can see between two models, there are actually difference. And of course, the tire lateral force generated between the tire and the road, they are also vibrating. But these are all overlooked in the simplified model. From here, we could see there is a big path difference between the two models. And again, in addition to the direct yaw moment, we also simulate the model under a sinusoidal steering input. It's active steering input. It's a sinusoidal input. The results here is a little bit interesting because in the direct yaw moment, the torque is just applied very sharply. This is used to simulate the collision avoidance scenario. In that case, we just apply a torque quickly. And here, for the steering input, we put a sinusoidal steering input on the vehicle. We could say because the steering input is applied on the vehicle gradually, so no transient process is excited. But we can still say there is a trajectory difference because in the rigid body model, the force is directly act on the vehicle body, so it moves very fast. But in the tire dynamics and suspension dynamics in considered model, when we have a control input, it needs a process. So the vehicle doesn't move like what we want. That's what we can see, even without any transient process, but we can still see there is a stable difference. So from the above research, we could see the effect of the tire dynamics on vehicle dynamics. Vehicle dynamic control is researched. We compare the bicycle model and the detailed vehicle model. The response of differential motor torque and steering demonstrates that the bicycle model is suitable for vehicle path evaluation with moderate driving conditions. That means if we don't put a harsh torque on the vehicle, we give it a moderate or gentle steering input, and the vehicle speed is not such high, the bicycle model is okay because the tire dynamics is not very significant, very obvious in this kind of the moderate driving conditions. That's okay. This is what we do in the autonomous industry. I talked with some industry partners. They can only test the vehicle controller with below 90 or below 60 kilometers per hour, because when the vehicle speed becomes higher, the controller, which is generated by the simplified model, doesn't work. That is because when the vehicle speed becomes higher, the dynamics becomes more complicated. So yeah, when the vehicle requires higher torque and sharp torque, this really happens when we do the collision avoidance, where we need to give it a very sharp input. This simplified model is not very sufficient to represent the dynamics. So we really need to develop a new and more representative models to do the autonomous vehicle research. Yeah. Thank you for listening. That's my report. Thank you.
Okay, thank you, Dr. Zhou. Thank you for your nice presentation. Okay, now I would like to invite questions from our audience, please. Okay.
In your speech, you mentioned that you designed one PID controller. I want to know what parameters this PID is controlling.
The vehicle speed. Vehicle speed, yeah. Yeah.
Okay. And in your speech, you use the sine signals to control the steering process. And other frequency sine signals that you have tried? Any different performance that you can see?
If actually for the sinusoidal wave, if we just apply a sinusoidal input, they are not very much transient process. We can still see the stable difference. If we try kind of higher frequency of the sinusoidal, it means we put it in a faster way. If it's a high frequency, the stable difference will be higher.
Okay.
Because we do it faster, the lateral force is larger. And if the lateral force is larger, the tire dynamics becomes more obvious.
Okay, thank you.
Yeah, thank you.
Okay, thank you. Any more questions, please? Okay, Dr. Zhou, I have a question. Actually, not really a question, just a comment. When you try to analyze the lateral stability of a vehicle like this,
Yeah.
fundamentally from beginning, you shouldn't really use that bicycle model, because the bicycle model does not have the degree of freedom in loading. Okay.
Yeah.
So, if you really want to discuss about the lateral stability dynamics, then the half-car model you use should consider to add the degree of freedom of rotation, the row of the vehicle.
Yeah. Yeah.
So that's pretty obvious. Okay.
Yeah, thank you.
That's my
thank
comment. And any other questions, please? Yeah, okay, just a second.
Okay, yeah,
You
seems
mentioned
interested.
you use the tire body. For simulate the tire body, you use the translation and rotation springs and damping. I want to know how to determine such parameters like springs and dampings.
By test, actually, there is a book with it names the tire dynamics and vehicle from the magic tire model. So they have a huge book. All of the parameters are tested in there. So here we actually didn't test it because we don't have the equipment. The parameters are just published on journal papers or with a book. We just adopt it. We use the parameters of the model directly and compare the difference. They did it in a very traditional way. That is 20 years ago. It was just a traditional vehicle without the in-wheel motor considered, without the autonomous scenario considered. So we can just kind of adopt that model to research autonomous and in-wheel motor applications.
Okay, thank you.
Yeah.
Okay, thank you. Okay, any more questions? If not, thank you very much, Dr. Zhou. So
Yeah, thank you.